electric field from continuous charge distribution. Continuous charge distribution is a little different than electric field from discrete charge distribution. So first let's maybe see if we can understand what this is before we start solving any problems. What you have done so far is you've looked at discrete charge distributions. And here's an example of it. So let's say you have some Q1, then you have another Q2, maybe you have Q3, Q4, let's do 5, Q5. And if you wanted to figure out the total charge, and let's say that this is the charge that sits on some kind of an object, so let's draw some object here. All right, so this is how the charge is distributed. You have 5 different charges. If you want to find the total charge, then what you would do is you'd have to add them up. So you'd have sum of all of these little QI. So you'd have Q1 plus Q2 plus Q5. Now, discrete and uniform charge distribution would be similar, but then you have all of the charges being the same and equally spaced. So you would have, here's an object, and let's say this object is charged just in that way. So you'd have 1, 2, 3, 4, 5 again, but now each one is just Q. Each one has the same exact charge. So if you want the whole total charge, you could still do I, and then you have Q1, Q2, Q3, but since they're all the same, this amounts to nothing else but 5 times Q. Now what we want to do is we want to look at a continuous, actually we will only do continuous, actually no, there's going to be a problem where your charge distribution is not uniform, but anyways, continuous charge distribution, continuous charge distribution. So in this case, what you have is, in reality, there's no such thing as a continuous charge distribution, because that you go all the way down to like electrons, right? And then you can stack up electrons next to each other. So you're always going to have discrete charge distribution ultimately, but to a very good approximation, you can run many things in terms of continuous charge distribution. Now, to try to visualize, to have a picture of that, suppose you have an object and the object is charged in a way that the charge is continuously distributed. So let's say you place a charge here, another one here, another one here, another one here. If this object has a continuous charge distribution, then if you were to zoom in and look at, you know, what's in between, what's here between these two charges, well, no charge. There's no charge here. What's here? There's no charge here. At this location between the two charges, only I have charge here, 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 and here. This is a discrete charge distribution. There's nothing in between. But for a continuous charge distribution, what's in between these charges here? More charges. You have more charges in between. This is a continuous charge distribution. And what's, if you were to ask the question, okay, fair enough, but then what's in between, you know, these two charges here, right? What's in between these two charges? Well, more charges, right? You have more charges here, more charges here, more charges here, more charges here. And in fact, how many, you know, can you zoom in and ask how many, what's between these charges? Sure, more charges. So the concept of continuous charge distribution is that it's like looking at a line and points. Right? How many points do you have in a line segment? Infinite number of points that you have in a line segment. So how many charges do you have in a continuous charge distribution? Infinite amount of them. But at the same time, what is the size of a point? Well, not that much. So what's the size of a charge in a continuous charge distribution? It's infinitesimally small, just like a point. It's not that point is non-existent. Point, it does exist, but its size is infinitesimally small. Same thing with a charge in a continuous charge distribution. It's infinitesimally small. So so you can't just label this thing as Q. Each charge in a continuous charge distribution is not Q, but dQ, infinitesimally small. And so if I want all of this, then I really have to do a sum. So if I want Q, big Q, I have to add up all of the little dQs, and that would be your integral, right? Now dQ, in physics, d of anything, dQ is a little bit of Q. If it's dx, it's a little bit of x. If it's dy, it's a little bit of y. If it's dl, it's a little bit of l. And how much is it? This little bit, it's infinitesimally small. Not infinitely small, because infinitely small would be nothing, but infinitesimally small, there's a difference there. All right, now this is a sum. So you add up all of these little bits. If you add up all of the little bits of q, then you end up, if you add up all of the little bits of q, then you end up with big Q. All right, so continuous charge distribution, and we will typically consider uniform continuous and uniform charge distribution. All right, I give you the concept of continuous charge. Now, here's something that is going to be useful. Let me see what I'm at. This is 100%. Let's be at 100%. Okay. So, charge density, the concept of charge density. All right, in 1D, you're going to have linear charge density. And it's just like any density, like the concept of density is mass over volume, right? So it's what you're used to. So for the charge density, you're going to have charge over, well, if it's linear, length. So the symbol for the linear charge density is typically lambda, and lambda is charge over length, since you're in 1D. And this amounts to, often enough, well, sometimes you can get away with writing just, well, let me do it proper. So this is dq dq dl, which sometimes may just be stated as q over l. If it's a uniform charge distribution, then you may get away with that. That's not always the case. So I'm going to put this put this in parentheses. Often it's the case, it's not always the case. So in 2D, surface charge density, that would be, the symbol for that is sigma, and this would be charge. How much charge do you have per surface? And so that would amount to dq over dA, a little bit of A. A stands for area. And I'm going to add 3D to this. I don't think we're going to do anything with 3D, but I'm going to add 3D to this. So volume charge density, volume. I think if we were in 3D, we just call this thing charge density. I don't think we add volume, but I'm going to put volume charge density. And this would be rho is the symbol we use for it, and this amounts to, as you probably have guessed by now, charge over volume. And this is something you're more used to. It's just that you used to have mass over volume. That was your density. And so here you would have dq over dv, where v stands for volume. And again, this might, in a specific problem, amount to q over a, but it may not. So I'm going to put this in parentheses, and this might amount to, I'm putting like approximately because it's not, anyways, this amount might amount to q over volume, but it might not. So lambda, I think I misspelled it. I think it's LA, lambda, sigma, and rho. All right, so what else? A is the area, and B is volume, L is length. So this is going to be useful, and specifically we will do 1D. I think we may touch, we're going to do 1 and 2D. I don't think we're going to do 3D, but I may be wrong on that one. In any event, we're going to do 1 and 2D. So now that we have all of this, we have the charge density defined, and we have put this into some kind of a mathematical expression. I have given you a case for continuous charge distribution with this expression here. Remember, integration is just summation. I'm going to put this here. Integration is just summation. That's going to be very useful in physics. And the first problem that we have is this one here. So let's zoom this, make this a little bigger. So derive an expression for the electric field along the y-axis. You have a rad, and along this rad there's a charge that is uniformly distributed. The charge distribution is continuous. It's not discrete, but continuous. And the question is, what is the electric field at any point along the y-axis? So let's go ahead and try that. All right, so let's first see if we can understand the situation. We have a charge that is distributed along a certain length. So some kind of an object, some kind of a rad. And within this we have a charge. We have the continuous charge distribution. I'm going to draw only a few pluses, but each plus should be like a point along the line. So there should be infinite number of little pluses. Each one is a letter dq. I'm looking for the electric field at certain height along the y-axis here. I call this A. So along some point A here. Well, so let's take this little dq here. Let's take this little dq. This dq contributes at this location to the electric field. Since it's a positive charge, is it a positive charge? We're going to say this is a positive charge. It doesn't really specify whether positive or negative. Let's just say it's positive. So this little dq contributes to the electric field at this position, and that little dE points in this direction, right? Because then when I go to the next dq, here's my next dq. This little dq contributes to the electric field at this location, and that gives me here another dE. The next dq does the same thing, contributes a little bit at this location, gives me another dE. And then next one, next dq does the same thing, contributes a little bit, gives me another dE. And then this one here gives me another dE. And so on. So of course what I'm looking for is the total electric field over there, but the total electric field would have to be the sum of all of the little dE's. So if I want to add all of the little dE's, then I have to integrate them. And how many little dq's do I have here? Infinitely many. How many little dE's do I have here? Infinitely many. So I have to add all of them up to get the actual E. Now, these are vectors, so I add infinitely many vectors. All right, so this is what I'm dealing with. Now, if this is the case, then what I have to do is pick the most arbitrary, most general case and run the whole calculation off of it. So here's the point at which I want to find the electric field. It is distance A up above the beginning of the rad. Here's the rad. You never take, you always want to aim for the most general charge location. So pick one somewhere along this right here. Don't pick one that is here at the beginning, don't pick one that is here at the end, but pick the most general case. So maybe some little dq right here. All right, you're gonna pick this little dq, and this little dq is going to be a certain distance away from your point of interest. Let's call this r. And it's going to produce an electric field in this direction, dE. Now the length of the rad is L. So I'm going to put here L. This starts at 0. This thing, here's the axis, and the axis continues. And let's label this as x-axis because that would make sense. So I start at 0 with my x-axis, and this thing runs. I hit L at this location, and then the story continues. Here's x. So what I could do is, it would make sense for me to label, if I have A here, I have R here, it would make sense to label this distance here as well. Let's just label it as x. So I could label it as anything I'd want. I could put M here, but I'm gonna put x, right? So the distance here is x, that's R, that's A, this is 90 degrees. So if the equation for the electric field normally is kq over r squared, then now the equation for the E is going to be k dq over r squared. But there's there's a directional component to it. So I'm going to put here vector r hat. I should explain r hat. So r hat in this case is just points along the r vector. So r vector points from here, wherever you charge is, to the point of interest. This is r. That's r vector. I'm going to put arrow above r to indicate this is r vector, and therefore r hat, which is, it's a directional vector that simply points in the same direction as big R, but its value, its magnitude is just 1. So that's r hat. Right, and r hat is going to be in the same direction in which DE points. So they point in the same direction. Sometimes this equation is expressed as in the following way: k dq over r cubed r. Because then I have r here and I have r cubed here, so it gives me r squared in magnitude wise, and then I don't worry about little r hat, but instead I have, you know, this whole r that points like this, and this r points in the same direction in which DE points. So I could also do that. All right, so I have the equation now. Which way should I go? Let's just, okay, so DE, let's DQ, let's figure out DQ, let's figure out R. Let's take this equation here. This is what's important to me. I'm going to rewrite this. I want the magnitude here. I don't have to worry too much about. Actually, what I want to do is I'm going to get rid of that, and instead I'm going to take this. And here's why. So DE is going to become K dq over r cubed, and then I have rx comma ry, because that's my r. And let's take it a little farther here. So this then becomes, okay, so it's a vector equation, dq over r cubed, and then what's rx? Well, rx is just x, and what's ry? Ry is just a. So what I can write is I can then write dex is going to become k dq over r cubed times x, and dey is going to become k dq over r cubed times a. So I found an expression for the dex and dey, and maybe I'll put it in the picture here. This is dex, and then dy points up like that. So I'm gonna, let me see if I can put it here. Dy 90 degrees between them, right? So if I want to find electric field here, then I have to find the x and y components of it. So let's maybe slide it this way. So well, let's do it one at a time. So maybe first we'll do dx, right? Dx, I'm gonna rewrite this. This is k dq over r cubed times x. Now dq, so remember that the linear charge density, which is constant in this case because this is a uniform distribution of charge, is dq over dl, and that of course gives me an expression for dq, which is lambda times dl. So what I can do is I can write dex equals k times, instead of dq I'm going to have lambda times dl over r cubed times x. But now I want you to think about this dl. So dl, that's a little bit of the length L. Right, now the length L starts here at 0, goes all the way here. So the this is a little bit of dl, and 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 this is a little bit of dl. What does it amount to? It just amounts to dl is effectively the same as dx, right? What's dx? Well, this is a little bit of dx here, this is a little bit of dx here, this is a little bit of dx here, and this is a little bit of dx here. how large is dx? Infinitesimally small. How large is dl? Infinitesimally small. They point in the same direction along the same length. So dx, I'm gonna put here, dl is the same thing as dx. So what I can do is I can then write dex equals k times lambda times, instead of dl, I can put dx times x. I have that divided by r cubed. Now r, so r squared equals a squared plus x squared, right? Which gives me an expression for r, a half to a half. If that is the case, then r cubed would have to be a squared plus x squared to 3/2. So now here on the bottom, instead of r cubed, I can put a squared, which, well, that a is a constant, plus x squared, and all of this to 3/2. This looks to me like I can integrate this, because if you look at it, I'm going to put here in blue, this is a constant, a is a constant, k is a constant, and then the only variable that I have is x here and x here, and I'm going to integrate with respect to x. So this is something I can work with. So I'm going to rewrite this as ex is just the sum of all of the little dex's, and that amounts to the integral k lambda, and then I have x dx over a squared plus x squared, and this thing to 3/2. Right? And so then ex, I'll simplify it a little, becomes k times lambda, because these are constants. Right? Charge density is constant because the charge is uniformly distributed. Then I have x dx over a squared plus x squared to the 3/2. And at this point, if you want to, you can go ahead and do this integral by hand, or you can just use software to do the work for you, which is exactly what I'm going to do. I mean, it wouldn't be too difficult to figure out what to do with this, but it's just not necessary. Just use the software and figure out what this becomes. So I have k, I used my calculator to do this one for me, minus 1 over a squared plus 4. Yes, so plus 4, and then this is to a half, so this is a square root. And then my limits. So I'm integrating along the x, right? Now where do I start? I start here at 0, and how far do I go? I go all the way here till I get to L. So I integrate from 0 to L. So this is from 0 to L. When I plug in the values, what do I get? So I get this. I probably should have, well, so it's k times lambda, and then 1/2 minus 1 over square root of L squared plus 4. There's a 4 here. Let me write this 4 a bit better. Oh. Well, all right. So L squared plus 4 square root of this thing here. And this is in parentheses. So I found ex. Now you could do a little more with this, because what you could do is you could now write that lambda is just q, the total q, whatever the charge there is, over L, and so you would then have that ex becomes k q over L times, and then you have half minus 1 over L squared plus 4 square root of that. Nope, my calculator lied to me. So let's see. It didn't look right. So I'm gonna get rid of this thing. And I'm gonna get rid of this thing. And the error comes in at this place right here. So I'm gonna get rid of this. There's no 4 in here. That 4 seemed odd. But instead of 4, so I did it by hand, but instead of 4, what I should have, where was it? I should have here x squared. this should be x squared. And then that makes a little more sense because I put L in here. So when I put L into x, what I should end up in the end with is k lambda times, and then let's see, 1 over a minus 1 over a squared plus L squared square root of it. Yeah, that's better. It's much better. And so now if I do use this, then I can have an expression for x component of the electric field as kq over L times, and then in parentheses here, 1 over a minus 1 divided by a squared plus L squared square root of it. Okay, so this is the x component of the electric field at the point of interest. Maybe I'll put this thing in the box. Yeah, it's good enough. That's the x component. So what we found is this. Now we still have to find the y component. So I'm going to run this through, finding y component, and the y component is this expression here. So k dq r cubed times a. All right, so let's move this out here. So the ey is k dq over r cubed times a. And now a couple of things that we can already steal from the previous part. So dq, that's lambda times dl, but dl is just dx, so this becomes lambda dx. And the other piece that I have here is that r cubed was a squared plus x squared to the 3/2. Let's make sure that that's what it was. To the 3/2. Yes, okay. All right, so then, well, before I do that, ey is the sum of all of the little deys, which gives me k dq, but instead of dq, I'm going to have, so let's go back, instead of dq, I'm going to have lambda times dx times a, and then on the bottom r cubed, which is a squared plus x squared, and then this is to 3/2. Now a is a constant, k is a constant, lambda is a constant, so what I end up with, I need the integral here. What I end up with is k lambda times a, the integral of dx over a squared plus x squared to 3/2, and then I integrate from 0 to L just like before, and this gives me ey being, all right, so let's try my calculator one more time. Well, what I have here is k lambda times a, and times, once the integral is done, and what I'm getting here is that this becomes 1 over a squared, and I have a squared plus L squared, but square root of this whole thing here. Now, before I underline this thing, I'm going to check and see if this is actually what I should be getting. So it is, but the answer that is shown to you is in a modified version. So let me do that so that you don't have you're not confused by it. So what I can do here is I can write that this becomes k lambda times, well, I have 1 over, and here's a, sometimes students will ask me about this, what happened here, how is that working out? So what I can do is I can pull, oh, which way was it? One of these two, I'm going to pull one of these out of the square root, but let me see which one I should pull out, so that I have the expression that you have in your worksheet. Well, I found another error here. Well, anyways, long story short, this should be right here. I'm missing an L. Was it L or L squared? It was L. So I'm missing an L here. This should be an L. So then that L carries over. And then what I have here is this stays, but I have to pull L out. So here's what I'm going to do. I'm going to write L squared, and I'm going to write a squared over L squared plus 1 square root of that. All right, so I'm factoring out L squared, and then what that allows me to do is to rewrite this like this. times L on the top over A. And then when I take L out, I'm going to have L, because this is the square root. And I have the square root here, that's A squared over L squared plus 1. And I'm going to rewrite this here, EY equals, so L nicely cancels out. Now I have what you have in your answers there, K lambda over A times, and this is 1 over, and you have square root of A squared over L squared plus 1. Okay, so I have E, Y, and I have EX. Let me see if I can catch them both in one place. Yeah, there we go. I have EY and I have EX. And that is for a charge distribution, linear charge distribution up to a length L of a specific charge Q at a location at this point here, where that's perpendicular distance A going up, and the electric field here would have some X component, some Y component, and it would point, if it's a positive charge distribution here, then it would point somewhere in this direction. That would be E, and its components would be, well, this is EX comma EY. So anyways, there's plenty here for you to look through. And then let's see if I can assign you something. Yeah, so the problem we just solved was this one here. There. This is the problem we just solved. We found an expression for the X component, EX, found an expression for the Y component, EY, and that was for this specific charge distribution up to length L. Now, I want you to try this one, problem 2. Right, so derive an expression for an electric field at point P, some vertical distance A up over a line, finite line. It extends to distance L in a positive X direction and distance minus L in a negative X direction. Now, obviously, these two are very similar. So what you can do is you can take everything that you've seen in the solution for the first problem and apply it to the second problem, but you're going to have to change the integration limits, and you're going to have to think about the components of the force. So there's a certain amount of symmetry. Maybe you'll see through it. We'll see how it goes. In any event, I will go over this in a class next time I see you, but you should still try this, and your homework is to try to do this. So this problem number 2, which is this one here, and then previously I assigned whatever I assigned from the other video. So combine this one, this problem 2, with whatever was assigned from the other video. Okay.